Okay, so let us get back to axiomatic set theory. So we ended the previous video here. Remark 21. So this remark says that the subset relation and the element relation are different. We know that they are different, but this is something we have to keep in mind. We should not make mistakes and we should not confuse between these two. For example, 2 is an element in the set this, and this singleton set is a subset of this set are true. These are true statements, whereas these are not. So this is something we should keep in mind. Okay. Now we have seen so far 4 axioms. It's the time we see the 5th one, which actually is related to the set builder notation that we have already seen in naive set theory. So this is axiom 5. It has a name. It's known as the Axiom of Specification. So the statement goes like this: let A be a set and for each element x in A, let Px be a property pertaining to x. That is, Px is some statement that depends on x. That is, Px is either true or false. As x changes over A, the statement Px changes. So for a given x in A, Px is either true or false. Then the axiom says there exists a set which is denoted like this: x belonging to A such that Px is true, and the this set is defined to be exists a set that consists of those elements of A for which Px is true. Okay, so from a given set A, we are basically collecting some elements, namely those elements that satisfy this property P together, and this axiom says that that collection will be a set. That is, for any object y belongs to this set such that Px is true if and only if y is an element in A and Py is true. So it has the name specification because using the property P specifies what are the elements of A that are to be taken together to form the set. That is specified by the property. This axiom also has another name. This axiom is also known as the Axiom of Separation. It separates the elements of A which satisfy P from the elements of A which don't satisfy P. Okay. Note that this set Px is true is always a subset of A. Why? It's really easy to see why it is so. Because if you take any element in this set, for that element, it first of all has to be in A, and then P of that element must be true. That statement must be true. But in any case, that must be an element in A. So any element in this set is in A. That's why it is always a subset of A. Though it can be as large as A and as small as the empty set. It will be equal to A precisely when every element of A satisfies the property P. Otherwise, in the other extreme case, when no element of A satisfies P, then it will be the empty set. Right. Yeah, one more thing is that one can verify that the axiom of specification, since these are new axioms that we are introducing in the class of sets, every time we introduce something new, we have already said this, discussed this, that we have to see whether the new concept satisfies the axiom of substitution or not. If not, then there is something wrong with it. In this case, it satisfies the axiom of substitution. Works for specification. In this way, if A equals A prime, where A and A prime are two sets, let me write that. are sets, because otherwise it's not clear. Then this set, the set of those elements of A for which Px is true, is equal. I won't have space here, let me write it here. This set will be equal to the set of the elements in A prime for which Px is true. And this is very easy to see why this is true. These places marked with Y, they are there in Tau's notes. Okay. Usually these Y questions are quite easy to answer, so some of them I am just leaving. But as we go further and further into this notes or book, we will see that it will not be so easy. It will not remain so easy. So in those times we will supply you with a proof. Okay. We sometimes denote this set x belonging to A such that Px is true by this, where we replace the colon by a vertical bar. Both of them mean the same thing, such that. Right. Now, there is a very simple example illustrating this. So basically what this axiom says is just what we already know about the set builder notation for specifying a set, which allows us to specify a set with the help of some property P. Okay, now here is an example illustrating this. This is example 22. Let S be the set of the first 5 positive integers. Then the set of those elements in S that are, say, less than 4 is the set consisting of these 3 elements. It's easy to see why this is so. B, let me denote another set by B, which is the set of those elements in S which are less than 7. Say. All the elements in S are less than 7. So this is equal to S. This is the case, this case, where this set can be as large as the given set. And there is another set C, which is the set of those elements in S which are less than 1. There is no element in S which is less than 1. So this is the other extreme case. It's the empty set. Right. Okay. Now, once we have this axiom of specification, we can now define intersection. So this is the next definition. This is definition 3.1.23. The intersection S1 intersection S2 of two sets S1 and S2 is defined to be the set of those elements in S1 which are not in S2. Okay, note that this definition is somewhat slightly different from the one we have seen in naive set theory. It defines S1 intersection S2 as the set of those elements in S. Oh, sorry, what the hell have I written? Sorry about this. I defined difference. X belongs to S2. Sorry about that. It defines the set or the intersection as the set of those elements in S1 which are also in S2. Okay. One can, however, we can clearly see that this definition and the one we came across in naive set theory, they are same. One can see that for any object y belongs to the intersection if and only if y belongs to S1 and y belongs to S2. Right, now there is here again, since this is a new definition in this series of videos, okay, although we already know what intersection is, but now in our axiomatic treatment of set theory it's a new definition. So then again that thing comes, axiom of substitution. So regarding that there is a remark. This is item number 24, and the remark is just this. Intersection means the concept of intersection satisfies the axiom of substitution because it is defined in terms of more primitive notions which are known to already satisfy the axiom of substitution. Why? Because you see, you look at the definition of the intersection, it is defined in terms of the fifth axiom, axiom of specification. We have here, in this case, the set A is S1 and the property P is the element belonging to S2. So in that way, using the axiom of specification, we have also at the same time, we can see from that axiom that this intersection is actually a set. that axiom guarantees that this is a set, this collection is a set. Further, since we already know, or we have said here, that the axiom of specification, the set that is given by that axiom, that satisfies the axiom of substitution, and since intersection has been defined in terms of that, so it also satisfies the axiom of substitution. The axiom of substitution in case of intersection is just this: if you have three sets like this, A prime and B, and A is equal to A prime, then you have to make sure that A intersection B is equal to A prime intersection B. A similar statement can be made with A, B and another set B prime which is equal to B. Okay, so that's the axiom of substitution in this case, in case of intersection. But we need not see that since it's already satisfied for specification, so it will automatically be satisfied by intersection. Similarly, for any new definition in the class of all sets that is defined in terms of some already defined notion will satisfy the axiom of substitution. And will not be explicitly mentioned anymore. We are not going to be bothered about this anymore. Right. Now naturally, because of a new definition, we need a new example, which is something quite easy. You already know this. Of this example is number 3125. The set, this set and this set, they have the intersection 1, 2, like that. These two sets 1, 2 and 3, 4, they have empty intersection. Okay, now there is a remark regarding the word and, the use of the word and here in intersection. And it goes like this: one should be careful with the English word and. Rather confusingly, mean either union or intersection. It can mean either union or intersection. How? Let's just see. For example, if we say, oh, depending on the context, for example, if we say boys and girls, then we mean the union of a set of boys with a set of girls. That is clear from the context that we have to take the union of a set of boys and a set of girls. That will mean boys and girls. Because intersection in this case does not make sense. But if we say, we can say still something else using and it will mean intersection. Actually, that's what comes to our mind when we think of and. It means intersection, but in this strange case, it can mean union. Now, if we say single and male, then we mean the intersection of a set of single people with a set of males, because single women can also be single. So in this case it is intersection. Also, sometimes and can indicate addition. Now this usage is rather loose, but sometimes we also hear this. For example, two and 3 make 5. This type of loose statements are often used by us. While at the same time one can say the set 2 and 3 give this set, which is clearly the union of these two sets, or 2 and 3 give empty set. We cannot argue which one is true or which one is false, because these are not precise mathematical statements. Why? These statements have undefined things. 2 and 3 make 5. In what sense? These are not precisely defined concepts. These are vague statements that we have in our languages, not just English, in every language. The same thing can be said in multiple different ways, and at the same time a single statement can make different types of meanings in different contexts. So that is the problem. One reason we use mathematical symbols and not English words. I mean, we use words, but not in this vague way, is that mathematical symbols have precise and unambiguous meanings, whereas one must look carefully at the context to figure out what an English word means in a given situation. So this was the remark. So we have to be careful in using the word and. It's better to use, that's why we use more and more mathematical symbols, because they serve multiple purposes. One is that they make the thing precise, what we are trying to say. There is a unanimous decision among the mathematicians about the meaning of a symbol, and there is no confusion. The other purpose is that it shortens the notation. Whatever we write in mathematics using symbols, they can also be written using just English words as sentences. However, that will be, even if we write all the definitions precisely, then we don't have any ambiguity, but that will be extremely huge and unwieldy. So that's why we develop some neat notation to denote many things. So the symbols that we see in mathematics, they contain a huge amount of information in them. Okay, so that was the remark, 26th remark. Okay, now having defined intersection, we already know these things, but still two sets A and B are said to be disjoint if their intersection is empty. Note that this is different from A and B being distinct, that is not equal. This is something else entirely. For example, the sets 1, 2, 3 and 1, 2, 4 are distinct. They are not equal but not disjoint. It is because their intersection contains elements, whereas the sets empty set and empty set, it's not necessary we have to take different sets. We can take the same set twice. The sets are disjoint but not distinct. Not distinct clearly because they are equal, and disjoint because their intersection is still empty set in spite of being equal, and this is the only situation in which this can happen. Okay, now comes the definition of difference of two sets. So this is a new definition, and this definition can be made with the help of axiom of specification again. So this is item number 27.